Just a moment. Okay, it doesn't mean it. Oh, you can another one. Okay, sorry. Excellent.
Nice songs.
Just. Yes, I guess you could talk half an hour plus. It's just that you are.
No, I promise I will
More than an hour. Okay, I guess we can start. Yes, the first speaker is Sepehr, who's going to talk about faster algorithms for edge coding.
All right, thank you. Thank you everyone for coming so early in the morning, and thanks for the organizers, everyone who invited me. And disclaimer, it's not really extroverted. I'm not an extroverted person, so this is a talk. Okay. All right, so we're going to talk about edge coloring. And let's define the problem. You have a set of colors 1 to C. You want to assign colors to the edges of your graph, such that whenever you look at a vertex, the colors incident on the edges of this vertex are different. So this is a proper 4-edge coloring of this graph. Okay. I want to make sure any vertex, the edges that it sees, get different colors. Okay. So, and if another way, if you want to think about it, it means that each color class, set of edges that are colored the same, is a matching. Okay, good. All right, so in this talk, we are going to work with these parameters. N is number of vertices, M is number of edges, and delta is the maximum degree of the graph. So what do we know about edge coloring? The first simple observation is that you always need delta colors. No, I mean, if you have a vertex of degree delta, you have to color all its edges differently. So you need delta colors. Good. It's very easy to see that 2 delta minus 1 colors is always enough. You can even greedily color the graph that way. Whenever you are at an edge that doesn't have a color, you've used delta minus 1 colors for this vertex, delta minus 1 colors for this vertex. By pigeonhole principle, 1 color remains. Okay. This basically is greedy coloring on the line graph. Good. Other better bounds. I guess like 8 years ago, Shannon proved that, the same Shannon, proved that 3 delta over 2 colors always suffices. Okay, and I put an asterisk here because he even proved it for multi-graphs. Okay, but in this talk, we'll talk about simple graphs, and it's important that we are only focusing on simple graphs. And then there's this Vizing's famous theorem that says actually you only need delta plus 1 colors. Okay, so for edge coloring, the right answer is either delta or delta plus 1. Okay, and this is used, proved using this notion of Vizing fans and Vizing chains that I will not talk that much about. And good. And then finally, it was proven that actually you cannot even distinguish between the graphs that are delta colored or delta plus 1 colored in polynomial, or it's NP-hard, basically. So you cannot characterize which graphs need delta colors, which graphs need delta plus 1. And in some sense, this means that our focus in research has been mostly on doing delta plus 1 color. So the question we're asking in this talk is that how fast can you find the delta plus 1 coloring of a given graph? Okay, a purely algorithmic question. I give you a graph, output a delta plus 1 coloring. It always exists. Okay. So what do we know here? Actually, Vizing's approach itself really gives you an order mn time algorithm. Okay. And then this algorithm was actually formalized, works by Rao and Dijkstra and Misra-Gris that show that there are like very simple order mn time algorithms that find the delta plus 1 coloring of any graph. But then Arjomandi and also independently Gabo et al. Show that you can actually get something which is m root n time algorithm for this problem. Okay. And this remained roughly the best round time for many years until Cinnamon showed that you can shave off a square root log n factor from it. In fact, he showed that you should just analyze this algorithm a bit better. The recurrence itself is giving you m root n. You don't. So this log n was thrown in just for convenience. Basically. Good. So this is the bound we know. And if you've seen this m root n bound, sounds familiar with a bunch of other bounds for graph algorithms that you've seen from, let's say, this era. So are there better algorithms? We actually don't know. The only better algorithms we know are for special cases. Okay. 2 delta minus 1 coloring, the greedy corollary, you can do it in m log delta time. It's actually a good exercise. It's not trivial to do this. Then Karloff and Shimois show that you can do delta plus root delta coloring in roughly O tilde m time. So you can do better than 2 delta minus 1 still in near linear time. More recently, there are lots of results that do 1 plus epsilon delta coloring. Think of them as some sort of an FP task or some approximation scheme in m poly 1 over epsilon time. Okay. Something that is relevant to our talk, actually people figure out that you can delta color bipartite graphs. So bipartite graphs always admit a delta color. You can find the delta coloring in m log delta time. Okay. And there's a very, very simple algorithm that does this when delta is a power of 2. Okay. That's a very good exercise to solve. When delta is not power of 2, it took quite a lot of effort to get this algorithm. And there are a bunch of other cases, low verbosity graph, things like that. But in general, we don't know actually better than m root n time algorithm. And this remains a barrier for since 80s. Okay. So what is this talk about? Let me tell you about our result. The first result is what I would like to call a near Vizing theorem in near linear time. And that's a delta plus log n coloring in m log delta time. Okay, so not exactly delta plus 1, but delta plus log n, so not that many more colors. And you can do it in m log delta expected time. And this is basically as fast as what you get through greedy, although this is randomized and this is expected. And the good point of comparison is that previously we knew delta plus root delta. Now we're shaving off this root delta to become roughly log n. Okay, there was a log n factor here already. But there are a bunch of main features for this algorithm I want to point out. One is that the approach has almost nothing to do with these Vizing fans and chains and the techniques used for proving Vizing's theorem. It does something somewhat entirely different. Okay. And that's the part that's related to sublinear algorithm. It really builds on the insights that have been developed in the last 2 decades for designing sublinear algorithms. Particularly, there are 2 real gems in sublinear algorithms, let's say, among many others. But there is one, this very nice streaming algorithm by Andrew McGregor that shows how you can reduce non-bipartite matching to bipartite matching. Okay. And there is this very nice sublinear time algorithm by Goer, Kapralov, and Khanna that shows how you can find a regular bipartite matching in sublinear time. Okay, this is, a perfect matching in a regular bipartite graphs. Okay. And we are going to use, let's say, ideas and inspiration from these 2 work to design the result that I talked about. I will mostly talk about this part because this is more concrete. I can show you exactly, in technical sense, what we are doing. But this is also equally important for this work. I'm happy to talk about it offline, at the insight or inspiration level, how it helped. And the nice thing about the result that I told you, it implies a bunch of corollaries immediately. One of them is, for instance, this. It now gives you an algorithm to find this Vizing's coloring, this delta plus 1 coloring, in quadratic time. Okay. So it means that now you can find delta plus 1 edge coloring in roughly n square expected time. Okay, or with high probability if you throw in another log n. This is now near optimal for dense graph. This is an order n square type result. So if your graph is dense, this is near linear in the input size. And this breaks through this m root n barrier, basically. It's a polynomial time improvement whenever m is larger than n to the 1.5. Let me show you this proof. This is a 1-line proof at this point, now that we have the other result. So find the delta plus log n coloring of your graph in near linear time. Okay. You have log n extra colors. Look at the color classes that are smallest and throw out their colors. Okay, so now you have a delta coloring, for instance, or delta plus 1 coloring. How many colors you throw out? You partition all your edges among roughly delta colors, okay? And you're throwing out log n fraction of them. So these many edges become uncolored, okay? Just pass them to Vizing's algorithm itself, the original Vizing's approach from the 60s. It can color every uncolored edge in order n time, okay? So Vizing's proof shows that any uncolored edge can be colored in order n time. You have these many uncolored edges, just pass them there. You get an algorithm with runtime mn over delta.
Starting with any valid coloring for the other edges, the Vizing's approach shows that you can.
Yes. Yeah, I had a slides for that and I removed them, but Vizing's proof is this. Give me any coloring of your graph, give me any uncolored edges. I can recolor order n edges so that now this new edge can be colored as well. Okay. And that order n edges is found in some sort of a mechanical way, like in linear time, you can find them as well. And once this quantity is at most n square, because m is at most n delta. Okay, good. So the moment you have this result, you can just improve Vizing's theorem right away. There's another corollary here is that you can get 1 plus epsilon delta coloring in m log 1 over epsilon expected time. Okay. Of course, you need epsilon to be slightly large. Okay. You always need epsilon to be at least 1 over delta because you cannot find the delta coloring. It's NP hard. But it needs to be log n over delta. If you remove this assumption, you'll just get a linear time algorithm for Vizing's theorem itself. But the point is that there are a bunch of 1 plus epsilon delta coloring algorithms recently. They're all having polynomial dependence on epsilon, or at least linear dependence. This is saying you can get it with exponential, with log dependence on 1 over epsilon.
So this in the previous corollary, even if you got a delta plus 2 coloring, it still gives only n squares.
You need delta plus, yes. Coloring that last m over delta edges is very hard. All right, so before I move on, I want to shout out to another independent concurrent work. These two works actually went on archive like within 2 days of each other, and we didn't know about each other's work. This is by Bhattacharya, Carmon, Costa, Solomon, and Zhang. And they find another way of breaking through this m root n time barrier for Vizing's theorem. And they have an algorithm that gets mn to the 1/3 time for delta plus 1 coloring. It's a very nice algorithm. They found a way to speed up this way that Vizing was coloring the edges using fans and chains to do that part faster than spending order n time in the worst case always. And a very quick comparison is that, well, their result is going to be faster when the graph is a bit sparser, specifically has these many edges. And ours is going to be faster, especially the delta plus 1 coloring result is going to be faster when the graph is denser. And eventually, when the graph is completely dense, we achieve like near optimal bounds. Well, this one is a bit always above the near optimal.
Are you saying that their algorithm is like a sublinear time way to color an edge, or like?
No, unfortunately, that's not true. Okay, so in certain settings, when you have enough number of uncolored edges and things like that, they'll get something which is faster than order n. Okay, think of it as a dynamic graph algorithm. On average, over all the edges they are coloring, and eventually that part breaks, and that's why they don't get an order m time completely.
So you cannot use their algorithm to sort of speed up yours.
Very good. Let me get to that. Yes, we can do the opposite. So these two techniques are almost entirely different. Like there is almost really no overlap between them. And beside the fact that they're working on the same problem, there was almost no similarity between the two. And we are focusing on two different ends of the spectrum. Like the delta plus 1 log n coloring algorithm, I told you, just color almost all of the graph in one shot, and then just applies Vizing's theorem like kind of trivially to the end. And it turns out you can combine both of these works together to get something which is strictly better than like the minimum of both runtimes. And you can get an n root m time algorithm by combining both of these works. And the way it works is that actually we use our delta plus log n coloring algorithm as a subroutine in something they had. And that you just replace it and you get n root n time. And this was an observation both of us made in a quick discussion. Both groups, I guess, 5 people. All right. So that's all I wanted to say about this other work. And now let's go back and talk a bit about what is our algorithm, how it works. So I'm going to really focus on this one. As I told you, the rest follows almost immediately. Delta plus log n in m log delta time. And the idea at a very high level is you want to color a matching from your graph, a large enough matching, because you can always color it the same. You pick a matching, you color it, you remove that matching, and you recurse on the graph. And what you want to show is that after delta plus log n iteration of doing this thing, you've just colored the entire graph. It's not going to be entirely true this way. Like at some point, we have to switch to do something else, but this is the idea. Okay? And the question is how we can find such matchings fast enough and how we can ensure that after, like it converges fast, you don't have to remove too many matchings before you can cover all the matchings in your graph. All right, so now let's talk about this sublinear time algorithm of GKK. And this was really our starting point. So these guys design a randomized algorithm. Give me a regular bipartite graph. It always have a perfect matching. And they show that you can find it in n log n time. This is truly a sublinear time algorithm. Okay, you don't need to read the entire graph. You can just find such a, like you can find it very fast. And this is really one of the true gems of sublinear time algorithm. This entire algorithm, its analysis is like 1.5 pages. It's very beautiful. Let me tell you the algorithm. The algorithm is this. You start with an empty matching. While it is not a perfect matching, you just pick an unmatched vertex uniformly at random. And you just do random walk, basically, meaning that you, let me show you an example. Let's say this is an unmatched vertex. You pick this vertex, you don't have to look at its neighbors. You just pick one of its edges going out uniformly at random. Okay. So now you're here, let's say these red vertices are matched. You just take the matched edge to go to the other endpoint. Then you again pick one edge out of this vertex. Okay, this is an unmatched edge. And just continue doing this thing. Let's say eventually you hit an unmatched vertex. Now this is an augmenting path. Okay. And you can augment, you can increase the number of matched vertices by 2. Okay, so you increase size of your matching. Instead of doing BFS and all sort of clever ways people have been doing finding augmenting paths, you'll just do a random walk. And what they show is that if the length of, if you have roughly k unmatched vertices, the length of the walk you have is n over k. And once you know this fact, computing that the runtime is n log n is trivial. You just sum up over 1 over k, kn to 1, for instance, becomes n. And the idea here that why this is correct is just write the Markov chain of this random walk, and you see that it's a strongly connected directed graph with the same in degree and out degree. So you can compute its stationary distribution easily. You can figure out the heating time, basically how long does it take for the walk to find another unmatched vertex. Okay. So it's very good, very strong, and you can solve the problem this way. So now this approach actually also gave them an edge coloring result for bipartite graphs. Why? Let me try to use this to delta color a bipartite graph. There is this fact that I hope you just believe from me. I will not prove it. Any graph that you give me, I can make it a delta regular by introducing multi-edges without increasing the number of edges in the graph asymptotically. Okay. So you can do this for any graph. Okay. So you can assume without loss of generality when you're delta coloring bipartite graph that you start with a delta regular graph. Okay. Although you will have multi-edges. So now when you start from that, what will you do? So you have a delta regular graph. You know you can find a matching in it in n log n time. Just go ahead and find a perfect matching. Color that's entire perfect matching with one color and remove it from your graph. You had a delta regular graph, you remove a perfect matching, you have a delta -1 regular graph, recurse. Okay. After delta step of this thing, you just emptied out your graph entirely. You have delta different perfect matching, you're coloring them differently, so you have a delta color. That's proof of correctness. Runtime, each of these operations takes n log n time. Okay. You have delta of them, and we assume that the graph is delta regular, so n delta log n is m log n. Okay. That's a delta coloring algorithm using the GKK approach. This is actually appear in their paper already. Okay. So we can do this to delta color bipartite graphs. Now let's see what we can do about delta plus log n coloring of general graphs, which was the result we are interested in. So how we can implement this strategy? Let's say where things go wrong. The first step that things go wrong is that you cannot allow multi-edges when you're working with general graphs. Multi-graphs are not delta +1 colorable. Okay? The moment you introduce multi-edge, you may not even find a delta +1 color. So you cannot make your graph regular, okay? But let's say you could. Then this GKK approach, it just doesn't work on general graphs, okay? It doesn't find maximum matchings because of general matching having these blossoms and offset constraints. But even if it worked, general graphs don't even have a perfect matching necessarily. If you have a delta regular general graph, it doesn't have a perfect matching. Think of a triangle, okay? So you will not be able to find a perfect matching. And that means that when you remove it, you don't end up with a delta minus 1 regular graph, okay? You may not even reduce your maximum degree. Okay? So these are the challenges we have to address if we want to implement this strategy. But there are two observations. One is that we really don't need to find a perfect matching. It may not even exist. Okay. We have to find a good enough matching, and I'll define it for you shortly. The other thing that was helpful is that we really don't need a sublinear time algorithm in each step. Okay? In the sense that we have enough time to pre-process the graph, spend some time, prepare the graph, and then after that, maybe you find each matching in sublinear time. Okay? And we are going to use both of these things. So what is the solution? We're going to define these things that, let me call them fair matching, okay? They are a distribution over matchings on maximum degree vertices of a graph, okay? So I'm not assuming my graph is regular anymore, okay? I'll work with the maximum degree vertices. This is a distribution over max degree vertices, matching over max degree vertices. And this distribution tries to match every maximum degree vertices almost equally. Like it tries to match almost all of them, and also is not biased toward, okay, this vertex never gets matched. Okay. Like if pictorially, let's say these are all the vertices, these are all the maximum degree vertices, you find a matching incident on these guys. And actually, it has this property. If you look at any vertex of degree delta, probability that it is not matched by this matching, it's roughly 1 over delta plus some tiny noise there. Okay. So you will try to basically treat all the vertices fairly. All of them have roughly the same chance of getting matched here. This is this definition of fair matchings that I'm defining. And one key technical part of the paper is to show that this random walk approach that Goel, Kapralov, and Kano had, you can work with an idea like that to sample a fair matching in roughly n log delta time. In fact, this is number of vertices with maximum degree delta. Okay, so the runtime of this algorithm depends on the vertices with maximum degree delta.
Does it again have this like same in degree, same out degree?
No, that's not true. Yes. And this random walk, you have to really change it. Like you have to be okay with finding alternating path instead of augmenting path. Sometimes you cannot extend the matching. You just change it so that next time you will find a better matching and things like that. And this starting here is that this is not a sublinear time algorithm. We actually don't get a sublinear time algorithm for finding fair matchings. This algorithm requires a pre-processing.
So the definition of the fair matching, so if suppose everything was delta regular, does it imply the size is?
The size is at least large. It's 1 minus 1 over delta, which is the integrality gap of matching polytope there, yes. The fractional matchings, not polytope. And this basically requires, proving this thing requires generalizing this GKK approach, the random walk approach from sublinear time algorithms to non-bipartite and non-regular graphs. And there are a bunch of challenges. If you have non-bipartiteness, now you have to handle odd cycles and blossoms. If it's not regular, the Akash was saying that you don't get, like the Markov chain you're getting is not a good Markov chain. It does not necessarily has like the same in degree and out degree. But it turns out you can add a bunch of auxiliary edges. Like you create a Markov chain, which is not exactly the Markov chain of your walk, but the beginning of the walk is the same between the two, and then you analyze it on the other. And then the main hard part is actually ensuring that all the vertices are treated equally, the same way in this one, which requires working a lot with alternating paths. So this algorithm finds a large matching relatively fast, and then spend all of its time rematching and unmatching things so that all vertices get roughly the same chance of having, like, being matched here. So in the remaining time, so this you'll do. So you'll use these ideas and you get this algorithm. But let me just tell you, now that you have it, you're more or less done. Modulo, like a lie that I have to tell you. I don't have to, but anyway. So the algorithm looks like this. You sample a fair, you have your graph, you sample a fair matching from it. Let's say these are the maximum degree vertices. This is going to be your fair matching. It's not going to be able to match all of them. Like there was a triangle here, and because this guy went there, you now have to figure out what to do with this vertex. But you're going to pick these blue edges, you color them, and you remove them from your graph. Okay. Now all of your vertices become degree delta -1, except for the unmatched one. So you have to do something with these guys. You're going to say that I will handle them later. You just pick an edge incident on them randomly for now and put them in some set F and say that I will figure out something to do with these guys later. So this edge, I remove it from my graph and put it in this set F. F is not being colored. Okay. Now my graph has degree delta -1. Okay. I will recurse on this graph. Good. And you continue doing this until your graph becomes empty. Once the graph is empty, you bring back these edges in the set F that you never colored. And you're going to just greedily color them using a new set of colors. Okay. And yeah, these are new colors, so you won't create a conflict with the matchings that you've colored already. Okay. So correctness analysis, very quickly. Up until here, you were using delta different colors. You remove delta matchings, and now you have to color F. And this you're going to do very like brute force-ish, like order delta F colors. Like you run greedy. In fact, even worse than greedy. You color them with 3 times the maximum degree. So now we have to figure out what is the maximum degree here. Okay, and look at how many times a vertex is going to remain unmatched and pick an edge. So what is the degree of a vertex inside this set F? If you're unmatched, you're picking an edge. But the probability that a vertex is unmatched when its degree is d is 1 over d. And its degree is going from delta to 1. So these probabilities are 1 over d. Sum of that is like ln of delta. Okay. So this statement is correct. But there is a big lie here. Edges have 2 endpoints. Like you may receive, you may have even been matched, but someone else is unmatched and picked you. Okay. So now you receive a degree even though this vertex is matched. So you have to handle that as well. And that ended up being actually non-trivial. Okay? But you can handle that. So the degree of vertices remains order log n, basically, regardless of whether they've been unmatched or someone else picked an edge to them, etc. So it means that at the end, this set F that you have maximum degree order log n with high probability. Which means that when you were doing the coloring in the final step, you only use order log n extra colors, which is going to give you delta plus log n color. All right, a quick runtime analysis. Again, the first part was when we were doing the matchings. Well, what was the runtime of fair matching? Number of max degree vertices, time log of delta. So think of on average, for each maximum degree vertex, you are spending log delta time. And each vertex is a maximum degree vertex in at most degree delta iterations. No? So each time it participates in this game, it loses 1 degree. So each vertex roughly participates in degree iterations, and in each iteration pays log delta time. So the total runtime for each vertex is degree times log n, and you sum up over all the vertices, it becomes m log delta. So the runtime for each vertex is m log delta for the first step. And the last step is just greedy coloring. In fact, you're doing 3 delta coloring, so you can color it in linear time. So you don't have to pay much time. Good. All right, so you do all of this, and you get m log delta coloring as well. And this is the entire algorithm. Okay. Modulo how you find fair matchings, I think I showed you everything, and except for that lie that I didn't show the analysis. This gives you delta plus log n coloring in m log delta time. Let me conclude. We show that you can find delta plus log n coloring in m log delta time in expectation. As a corollary, you just get an n squared time roughly algorithm for Vizing's theorem, which broke this m root n barrier. Again, let me mention this work of Bhattacharya et al., which they're getting mn to the 1/3. It gives a fast approximation algorithm. I think as a sublinear takeaway, to me, it was lots of the sublinear ideas that we have actually work beyond sublinear algorithms. The idea itself works even if the algorithm, if the sublinear algorithm itself is not working. So we didn't end up finding a sublinear time algorithm for finding fair matchings. Okay, I don't think you can find that, in fact, to be proportional to just degree of vertices that are like max degree. But still, you can use like some pre-processing. Now that we are using this sublinear time algorithm in some other setting, we can prepare the graph so that now we can use those ideas to solve the problem faster. And the natural open question at this point is that can we solve Delta+1 coloring in just near linear time? And that's all I wanted to say. Thank you.
Perfect time. Any questions? Comments? Yeah.
So, I'm curious to see if you could give some more ideas about how you derive this count of n delta, log delta for finding and matching among for finding this fair matching. Can you say more about it?
So I think at the high level, one observation was that what GKK algorithm is doing actually is rounding a fractional matching to an integral one. I think what that algorithm is doing is the way it finds a perfect matching is that it starts with fractional matching that puts 1/delta on every edge, and then it finds a way to round it to something which becomes perfect, okay? To become integral, okay? And now suppose you have a graph and look at the maximum degree vertices and put 1/delta on all of its edges. So there is a matching that match all these vertices now. This fractional matching matches all these vertices. On general graphs, that fractional matching has an integrality gap of roughly 1 minus 1/delta. Okay, so you have to lose that. But this algorithm that I was saying also is based on this idea of that you'll try to round that fractional matching, okay, using this random walk approach. And I'll be happy to tell you a bit more. The 1/delta part that you lose is coming from the integrality gap of matching, okay, like to handle the blossoms.
So a couple of questions maybe, but I'll ask one at a time. So 3 delta by 2 in multigraphs, what's the fastest candidate?
Good question. I think there was a paper in this soda this year by Abhishek Dhawan that I think he got something. I don't remember what it is, but should check that. And it might be near linear or even linear.
I like Sandeep fastest.
Oh, if your premise their input graph is the delta cargo, what's known?
I think it's become one of these like, it's not NP hard, but you may need quasi-polynomial time or something. It's one of these local search. So what is the class? I forgot. Not PPAD, but these classes that you know what is the answer, but finding it is hard. So it's like, it's not NP hard, but it's an extremely hard question that we don't expect to solve it in polynomial.
Any other questions, comments? Okay, let's thank Sepehr again.
You need to ask about Delta+1